Welcome to this session. Today, we'll dive into LeetCode problem number 264, ugly number 2. This problem challenges us to generate the nth ugly number, which is a number whose only prime factors are 2, 3, or 5. Stay tuned as we explore efficient approaches to solve this problem step by step. In this problem, we are working with a special type of number called an ugly number. An ugly number is defined as a positive integer whose prime factors are restricted to only 2, 3, and 5. To help visualize this, the sequence of the first few ugly numbers is given as 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, and so on. Notice that every number in this sequence is either a product of these prime factors or the number 1, which is considered an ugly number by definition. The task in this problem is to determine the nth ugly number in this sequence. For example, if n is 10, the 10th number in the sequence is 12. You will be given an input, n, which represents the position, and the output will be the corresponding ugly number at that position. Let's look at some examples to clarify the task. In the first example, the input is n equals 10. The goal is to find the 10th ugly number. As we saw earlier, the first 10 ugly numbers are 1, 2, 3, 4, 5, 6, 8, 9, 10, and 12. Therefore, the 10th ugly number is 12, which is the output. In the second example, the input is n equals 1. Since 1 is defined as an ugly number and is the very first number in the sequence, the output is simply 1. These examples demonstrate how the input n corresponds to the position in the sequence, and the output is the ugly number at that position. To further explain, the first ugly number is 1, which serves as the base case for the sequence. The problem also has certain constraints. The value of n will always be between 1 and 1690, meaning the solution must be efficient enough to handle up to the 1690th ugly number. The sequence is strictly increasing, and each ugly number is formed solely by multiplying the prime factors 2, 3, and 5. It's important to note that duplicates must be avoided in the sequence. For example, 6 can be generated by multiplying 2 and 3 in different orders, but it should only appear once in the sequence. For smaller values of n, a brute force approach might work, but for larger values, an optimized algorithm is essential to prevent timeouts and ensure efficiency. To solve the problem of finding the nth ugly number, we can start by considering a brute force approach. The intuition behind this method is straightforward. We would iterate through all positive integers and check if each number can be classified as an ugly number. A number qualifies as ugly if, after repeatedly dividing it by 2, 3, and 5, we are left with 1. This approach relies on the key observation that ugly numbers are defined by their prime factors being limited to 2, 3, and 5. However, there's a significant downside here. Since we're looking for the nth ugly number, we may end up testing a large range of numbers, many of which are not ugly. This results in a highly inefficient process. While the space complexity is minimal because we only check one number at a time, the time complexity is extremely high, making this approach impractical for large inputs. A more efficient alternative is to use dynamic programming with a priority queue, or min-heap. The idea here is to systematically generate ugly numbers in ascending order by leveraging the smallest number in the heap at each step. We start by initializing the heap with the first ugly number, which is 1. Then, we repeatedly extract the smallest number from the heap, multiply it by 2, 3, and 5, and add these results back into the heap, ensuring there are no duplicates by using a set to track already added numbers. This method works efficiently because the min-heap ensures that numbers are processed in ascending order, and the set prevents redundant calculations. While this approach significantly reduces the computational overhead compared to brute force, it does have some trade-offs. The time complexity is O, n log n, due to the heap operations, and the space complexity is O, n, to store the heap elements and the set of scene numbers. Overall, this is a much more practical solution, though the logarithmic overhead from heap operations could still be optimized further. An even more efficient method, and the one we ultimately use, is dynamic programming with pointers. This approach eliminates the overhead of a heap by using 3 pointers to track the next multiples of 2, 3, and 5 directly. We maintain an array called dp, where each entry stores an ugly number, starting with dp 0 equals 1. The three pointers, I2, I3, and I5, are initialized to 0 and indicate the positions in the DP array that will generate the next multiples of 2, 3, and 5, respectively. At each step, we calculate these multiples, compare them, and select the smallest value to be the next ugly number. This number is then added to the DP array, and the corresponding pointer or pointers are increment. By iterating through the array in this way, we efficiently build the sequence of ugly numbers. The key advantage is that this method ensures each ugly number is derived directly from a previous one by multiplying it by 2, 3, or 5. The time complexity here is linear, O(n), as we generate each number in constant time, and the space complexity is also O(n), which is required to store the DP array. This pointer-based approach stands out as the most efficient in terms of both time and space complexity. By avoiding the logarithmic overhead of a heap and focusing directly on generating the required multiples, it minimizes computational cost while maintaining clarity. The simplicity of using just the DP array and three pointers makes this method not only efficient but also highly scalable. For these reasons, we chose dynamic programming with pointers as the preferred strategy. While brute force and heap-based methods provided valuable insights, they were ultimately rejected due to their inefficiency or increased complexity. The pointer-based solution strikes the ideal balance between performance, simplicity, and scalability, making it the optimal choice for directly computing the nth ugly number. In this problem, we are tasked with finding the nth ugly number. Ugly numbers are positive integers whose only prime factors are 2, 3, or 5. For example, the sequence starts as 1, 2, 3, 4, 5, 6, 8, 9, 10, and 12. The brute force approach to solve this problem involves iterating through all positive integers and checking whether each number is ugly or not. To do this, we initialize a counter, count, to track the number of ugly numbers we've found, and start with current equals 1, the first candidate to test. We then iterate through positive integers, checking each one to see if it meets the criteria of an ugly number. We define a helper function, is_ugly number, that tests whether a number can be reduced to 1 by repeatedly dividing it by 2, 3, or 5. If it can, the number is deemed ugly. This process continues until we've identified the nth ugly number. The helper function is_ugly number is key to determining whether a number is ugly. Within this function, we repeat division by 2, 3, and 5 as long as the number remains divisible by those factors. For instance, if a number is divisible by 2, we keep dividing it by 2 until it is no longer divisible. We apply the same process for 3 and 5. If the result of this repeated division is 1, the number is classified as ugly, and the function returns true. Otherwise, it returns false. Once we have this helper function in place, we use it to check each candidate number in our loop. If the number is ugly, we increment the count variable to track how many ugly numbers we've identified. After checking each number, whether it's ugly or not, we increment current to move on to the next candidate. When our counter reaches the target value n, we know that the last number evaluated as ugly is the nth ugly number. However, this brute force approach is inefficient because we end up testing many numbers that aren't ugly, such as those divisible by other primes like 7 or 11. In this brute force solution, the data structures and logic are simple but have limitations. We use basic counters, such as count to track how many ugly numbers we've found, and current to iterate through the numbers. The helper function is_ugly number streamlines the process of determining if a number meets the definition of an ugly number by repeatedly dividing it by the factors 2, 3, and 5. This approach deliberately avoids advanced data structures, which makes the algorithm straightforward to implement and understand. However, while the simplicity is appealing, the solution is inefficient. Testing every single number up to the nth ugly number is computationally expensive, especially since the vast majority of numbers are not ugly. Let's look at a Python implementation of this brute force method. The is_ugly function first checks if a number is non-positive, returning false in that case. Otherwise, it iteratively divides the number by 2, 3, and 5, and finally checks if the result is 1. The main function, find_ugly number, n, initializes count and current and uses a loop to find the nth ugly number. The implementation continues by incrementing the current counter after each iteration, regardless of whether the number is ugly or not, and this process repeats until we reach the nth ugly number. Finally, the function returns current 1, which is the nth ugly number. For example, if we call find_ugly_number 10, the function will return 12, as that is the 10th ugly number in the sequence. However, while this code works, it is highly inefficient for large values of n. The time complexity is problematic because we test every integer up to the nth ugly number, including many that are not ugly. For each number, dividing repeatedly by 2, 3, and 5 takes log number time, and testing a large range of numbers results in an approximate complexity of n*log max number. On the other hand, the space complexity is 1, as we only use a few variables. Despite its simplicity, this brute force solution struggles with large values of n, such as 1000 or 10,000, where the sheer number of irrelevant computations becomes overwhelming. Given the inefficiency of the brute force approach, there are significant opportunities for optimization. One powerful technique involves using a dynamic programming or heap-based approach to generate ugly numbers in sorted order. These methods eliminate the need to test irrelevant candidates by systematically building the sequence of ugly numbers. For example, a heap-based solution can use 3 pointers or multipliers to directly generate the next ugly number without iterating through non-ugly numbers. With these optimizations, computation time is dramatically reduced, making it feasible to calculate even very large values of n efficiently. By avoiding redundant checks and focusing only on the numbers that contribute to the sequence, these advanced methods provide a much more scalable solution to the problem of finding the nth ugly number. Here, we define a class called solution with a method nth ugly number that takes an integer n as input. The goal is to compute the nth ugly number, where an ugly number is a positive integer whose only prime factors are 2, 3, or 5. We start by initializing an array called ugly_numbers of size n, filled with ones. This array will store all the ugly numbers in order. Next, we set up 3 pointers, i2, i3, and i5, to track the positions where the next multiples of 2, 3, and 5 will be calculated. Initially, all these pointers are set to 0. Additionally, we pre-compute the next multiples of 2, 3, and 5 by setting next 2, next 3, and next 5 to 2, 3, and 5 respectively. Now, using a for loop, we iterate from 1 to n1 to compute each ugly number. At every step, we calculate the next ugly number by taking the minimum value among next 2, next 3, and next 5. This ensures that we are always adding the smallest possible ugly number to the array. After determining the next ugly number, we store it in the current position of ugly_numbers. Then, we check which pointer was responsible for that number and increment it to move to the next multiple. For example, if the next ugly number came from next 2, we increment i2 and update next 2 to the next multiple of 2 using the updated pointer. Similarly, we handle the cases for next 3 and next 5. Finally, after the loop completes, the nth ugly number will be present at the last index of the ugly_numbers array, since the array is 0-indexed. We simply return ugly_numbers, -1, as the result. This implementation efficiently computes the nth ugly number using dynamic programming and 3 pointers to track the progression of multiples. By maintaining a sorted sequence of ugly numbers, we avoid recomputation and ensure the algorithm runs in n time complexity. Here, we are implementing a solution to find the nth ugly number in Java. We begin by creating an array called ugly numbers to store the first n ugly numbers, and we initialize the first element as 1 because the first ugly number is always 1 by definition. Next, we define 3 pointers, i2, i3, and i5, which will keep track of the current indices for the multiples of 2, 3, and 5, respectively. Initially, all these pointers are set to 0. We also initialize the next multiples of 2, 3, and 5 as 2, 3, and 5, respectively. Then, we use a loop to compute the next ugly number. Inside the loop, the next ugly number is determined by taking the minimum value among the next multiples of 2, 3, and 5. This value is then stored in the corresponding position in the ugly numbers array. Once the next ugly number is identified, we update the pointers and the corresponding next multiples. For example, if the next ugly number matches the next multiple of 2, we increment the i2 pointer and recalculate the next multiple of 2 using the updated pointer. Similarly, we handle the cases for the multiples of 3 and 5 accordingly. Now, if the next ugly number is equal to the next multiple of 3, we increment the pointer I3 and update the next multiple of 3 by multiplying the value at the updated index of the ugly numbers array by 3. Similarly, if the next ugly number matches the next multiple of 5, we increment the pointer I5 and calculate the next multiple of 5 accordingly. This process continues for each iteration of the loop until we generate all n ugly numbers in the array. Finally, after the loop completes, we return the nth ugly number, which is stored at the index n1 in the ugly numbers array. This implementation ensures that we efficiently compute the nth ugly number by leveraging the properties of the multiples of 2, 3, and 5 while maintaining an ordered sequence of ugly numbers. To find the 10th ugly number, we start by initializing a list called ugly_numbers with 10 elements, all set to 1. This list will eventually hold the first 10 ugly numbers as we calculate them. We also set up 3 pointers, I2, I3, and I5, all initialized to 0. These pointers track the current position in the sequence for multiples of 2, 3, and 5, respectively. Additionally, we define the variables next2, next3, and next5 to store the next potential ugly number for each factor. Initially, these are set to 2, 3, and 5, which are the first multiples of 2, 3, and 5. The next step is to iterate through the sequence, starting from index 1 up to n1. During each iteration, we calculate the next ugly number by taking the minimum of next 2, next 3, and next 5. In the first iteration, this minimum is 2, so we update the second position in the ugly_numbers list to 2. Since 2 came from next 2, we move the pointer I2 to the next position and update next 2 to the next multiple of 2, which is 4. At this point, the ugly_numbers list becomes 1, 2, 1, 1, 1, 1, 1, 1, 1, 1, and the state of our pointers and variables is updated accordingly. In the second iteration, we again calculate the next ugly number as the minimum of next 2, next 3, and next 5. This time, the minimum is 3, so we update the third position in the ugly_numbers list to 3. Since 3 corresponds to next 3, we increment the pointer I3 to 1 and update next 3 to the next multiple of 3, which is 6. The ugly_numbers list now looks like 1, 2, 3, 1, 1, 1, 1, 1, 1, 1. For the third iteration, the minimum value among the next multiples is 4. This value corresponds to next 2, so we update the fourth position in the ugly_numbers list to 4. We then increment the pointer I2 to 2 and update next 2 to the next multiple of 2, which is 6. At the end of this iteration, the list becomes 1, 2, 3, 4, 1, 1, 1, 1, 1, 1, and we continue calculating the next ugly numbers in a similar manner. In the fourth iteration, the minimum value among next 2, next 3, and next 5 is 5. This time, 5 corresponds to next 5, so we update the fifth position in the ugly_numbers list to 5. We then increment the pointer I5 to 1 and update next 5 to the next multiple of 5, which is 10. The ugly_numbers list now becomes 1, 2, 3, 4, 5, 1, 1, 1, 1, 1. Following this pattern, we continue iterating and updating the list based on the smallest value of the next multiples. Finally, after 9 iterations, the ugly_numbers list is fully populated as 1, 2, 3, 4, 5, 6, 8, 9, 10, 12. The 10th ugly number, which is the last element in this list, is 12. To find the 15th ugly number, we follow the same procedure as before. We initialize the ugly_numbers list with 15 elements, all set to 1, and the 3 pointers I2, I3, and I5 are again set to 0. We also set the initial next multiples, next 2 to 2, next 3 to 3, and next 5 to 5. Using the same iterative process, we calculate the next ugly number at each step by finding the minimum of these 3 values, updating the list, and adjusting the pointers and next multiples accordingly. After 14 iterations, the ugly_numbers list is fully populated with the first 15 ugly numbers, 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 16, 18, 20, 24. The 15th ugly number, which is the last element in this list, is 24. Here, we analyze the time complexity of our algorithm for generating the first n ugly numbers. The process begins with initialization, where we create a list of size n to store the ugly numbers, and initialize 3 pointers and their corresponding next multiples. These setup operations are constant time, except for the array initialization, which takes n. Next, the algorithm iterates n1 times to compute the next ugly number. For each iteration, we determine the smallest value among the next multiples of 2, 3, and 5. Since there are only 3 values to compare, this is a constant time operation, O1. Updating the pointers and recalculating their associated next multiples also takes constant time, as these involve straightforward multiplications in increments. With n1 iterations, the total cost for this step is n. Finally, retrieving the last ugly number from the array is a simple operation that takes O1 time. Combining these steps, the dominant term comes from the iteration, leading to an overall time complexity of n. The overall time complexity of the algorithm is n, driven primarily by iterating through n1 elements to compute the sequence. Now, let's turn to space complexity. The dynamic array, which stores the first n ugly numbers, requires n space. In addition to this, we maintain 3 pointers and 3 variables for the next multiples of 2, 3, and 5. These are simple variables and require constant space, O1. When we consider the space requirements in totality, the dynamic array dominates, resulting in an overall space complexity of n. This balance between time and space complexity makes the algorithm efficient and practical for a large range of input sizes. Let's compare this optimized approach to a brute force method. A naive solution would involve iterating through all integers and checking if each one is an ugly number by repeatedly dividing it by 2, 3, and 5. This process is computationally expensive. To find the first n ugly numbers, the total time complexity would be k*log k, where k is the largest number checked. Since k grows exponentially with n, this approach becomes highly inefficient. However, its space complexity is minimal at O1, as it only stores the result. By contrast, our optimized solution avoids unnecessary computations and directly generates ugly numbers in sorted order. With a time complexity of n and a space complexity of n, it is vastly more efficient for large inputs. The use of dynamic programming combined with multiple pointers ensures that we achieve linear time complexity while keeping the space requirements proportional to the input size. This makes the optimized solution a well-balanced and scalable alternative to the brute force method. When working with ugly number 2, there are several common mistakes to be aware of. First, it's crucial to understand the definition of ugly numbers. These are numbers whose only prime factors are 2, 3, or 5. For instance, 14 is not an ugly number because it includes the prime factor 7. To validate a number, you should repeatedly divide it by 2, 3, or 5 until it either becomes 1 or a remainder that cannot be divided further. Another frequent pitfall is relying on an inefficient brute force approach, which involves checking all numbers up to a large limit. This can lead to excessive computations, making the solution impractical for larger values of n. Instead, efficient approaches like dynamic programming or using a heap are necessary. Additionally, when using a heap-based approach, failing to track visited numbers can result in duplicate calculations and redundant heap insertions. To prevent this, maintain a set to ensure each number is added only once. It's also important to handle the base case correctly. Forgetting to initialize the first ugly number, which is 1, can cause logical errors. Lastly, avoid overcomplicating factorization. Instead of explicitly finding all prime factors of a number, focus on dividing it by 2, 3, and 5 repeatedly. Keeping these points in mind will save you time and help you avoid common errors in implementation. Now, let's discuss some insights that can be particularly helpful during interviews. A key idea to remember is that ugly numbers are generated by multiplying smaller ugly numbers by 2, 3, or 5. This recursive property is the foundation for optimized solutions, whether you're using dynamic programming or a heap. To optimize, you can use a min-heap or maintain 3 pointers for the multiples of 2, 3, and 5, ensuring that you always generate the next smallest ugly number efficiently. Be sure to account for edge cases, such as very small inputs like n equals 1, very large inputs, and scenarios where duplicates need to be handled correctly. When communicating your solution, emphasize why a brute force approach is suboptimal and walk through the thought process that leads to an optimized approach. Highlighting this progression can demonstrate your problem-solving skills effectively. Additionally, you may encounter related problems. For example, LeetCode 264 focuses on generating the nth ugly number, which is directly related. LeetCode 313 extends the concept to include an arbitrary list of prime factors. LeetCode 1201 deals with finding the nth ugly number for 3 given divisors, while LeetCode 204 explores counting primes, which involves understanding factorization and divisors. Recognizing these connections can give you an edge in solving variations of this problem. Finally, let's explore some alternative approaches to solving this problem. One efficient method is dynamic programming with 3 pointers. Here, we maintain pointers for multiples of 2, 3, and 5 and generate the next ugly number by taking the minimum of the values these pointers indicate. This approach has a time complexity of O, n, and a space complexity of O, n, as it requires a DP array to store the sequence of ugly numbers. While it uses extra space, it avoids the overhead involved in managing a heap. Another effective strategy is the min-heap approach. In this method, we use a min-heap to track the next smallest ugly number. After extracting the smallest number, we add its multiples of 2, 3, and 5 to the heap. This approach has a time complexity of O, n log n, and requires O, n, space. While it's slightly slower than the DP approach, it can be easier to implement in certain cases. Lastly, there's the brute force approach, which involves iterating through all integers and checking each one for ugliness. However, this method has a time complexity of O, n squared, or worse, making it impractical for larger values of n. While simple, brute force is best avoided when efficiency is a concern. Understanding the trade-offs of each approach will help you choose the best solution depending on the context. Great job following along. In this session, we tackled LeetCode problem number 264, ugly number 2, and explored how dynamic programming combined with auxiliary data structures like heaps can lead to an efficient solution. Remember to keep practicing and applying these techniques to similar problems. Thank you for watching, and don't forget to like and subscribe for more coding insights. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!